The simplest of those is called the D-type flip-flop, or just a D flip-flop. For now, let's skip the set and reset inputs. They're just extra control lines that are made available on this particular implementation. The essence of the D-type flip-flop is a D input, a Q output, a Q bar output that, notice the bubble, that's actually badly labeled, I realize. That's just a Q, but with the bubble, it guarantees that Q and Q bar are always going to output the opposite state. And we have a clock. And in this particular case, there's no bubble on the front, so this is a positive active clock. And so what that means is whenever I get a rising, or not what it means, the behavior of the D-type flip-flop is whenever it sees a rising edge on its input, it looks at what's on the D and copies it onto the Q, and it copies the complement onto the Q bar. Rising edge on the clock pulse, capture D, transfer it to Q. Goes back down, comes up again. This time the D is in a 1 state, and so we see the Q going to a 1 and Q bar going to a 0. So the state of the Q is telling you, looking at the state of the Q pin, is telling you what the state of the D input was the last time there was a clock edge. All right. What's going to happen if I do this? What am I, and then I put a series of pulses here on my clock input. What am I going to see on the output? So let's just walk through it. Assume it was a 0. That means my input was a 0. Whoops. Oh, it's not going to do anything. Q bar is what I wanted to grab. So Q is a 0. Q bar is a 1. So I've got a 1 on the input. I get a rising edge. What's going to happen to the output? The Q is going to go to a 1 because I had a 1 on the input. So when the Q goes to a 1, the Q bar is going to go to a 0. Q bar is fed back around to D, so now D is at a 0. Now, not on the next edge, but on the next rising edge, what's going to happen to the output? It goes to a 0, and then that goes to a 1. And so this configuration, so it's going to flip from a 1 to a 0 to a 1 to a 0 to a 1 to a 0. Every time we get an active edge, it's going to cause one transition on the output. And this is referred to as a toggle function. And sometimes you'll see a flip-flop with that's labeled as a T-type flip-flop. Has no inputs. It just has outputs. Well, it has no data input. Has just a clock pulse input and a Q and or Q bar output. And the function is exactly implemented like this. Every time there's a clock edge, it causes the output state to toggle, to change states. To toggle means to change states. So if it was a 0, it's going to go to a 1. If it was a 1, it's going to go to a 0. Yes? What's the difference? Oh, that's a very good question. What's the difference between the output and the clock? Shift it over a little bit. No, no, no. Be careful. Let's try and draw this out in time. So I get an edge and that causes a rising edge there. And then I go over a little bit, so I'll go over a little bit, and then I get a falling edge. What happens to my output? It keeps going. So I go over a little bit, it keeps going. Then I get another rising edge. Then it falls down. So what happens is, if you think of it in terms of frequency, I just did a divide by 2. At whatever f I have as the input clock rate, if it's coming in at a regular rate, I'm going to have f over 2 as the frequency on the output. Yes? Can you change the triggering to be on falling edges? For a device, no. But you can buy a device with a falling edge trigger. So it's just a different kind of device. You need to look into, I mean, if you're going to design, folks, I'm not going to have you designing with these things, but you're going to see these function blocks in functional schematics that describe the behavior of the subsystems in the microcontroller. And so you need to be able to look at these symbols and say, okay, I see how that's going to behave. And if this was a falling edge triggered, there'd be a bubble on the front of that input. And in fact, technically, for it to be edge triggered, there would be a little angled bracket indicating that it was edge triggered rather than level triggered. All right. Any questions about the D type? Yes.
Wait, sorry, do we use this to count, or do we use this to just have the frequency?
Well, we won't use it directly. Okay, we're not going to do discrete logic design, but within a half an hour, you're going to see circuits made of D-type flip-flops that do interesting things, and those interesting things will be things that you will do. You won't build them, but you will use them, and being able to look at that description and understand what the implications of that functionality are, that is what's going to be important. Any other questions on D's? Okay, then we'll move to the next most interesting kind, the JK flip-flop. Once again, let's skip the set and clear inputs because we're not going to focus on the discrete parts. So here we go. Here's the clock pulse input. What part of the clock pulse waveform is going to be interesting to us? Falling edge. The bubble says it's active low. The angle says this is an edge triggered device. So what we're going to be interested in are the falling edges on the clock. That is what's going to trigger a transition. And the transition in the Q, and here I got it labeled right, 2 Qs with a bubble. The Q and the Q bar output is going to be a function of what's going on at the J and the K. So to do that, let's focus on this part of the table. So let's start by saying, okay, we've got the J and the K in the high state. That function is described as hold. So this is the memory state, or hold a memory state for this particular kind of device. And I can then have, whoops, that's not what I wanted. I want the J and K, so when they're both low. When they're both low, and I have a falling edge, because everything happens on falling edges, then it's just going to keep, whoa, boy, the bar got out of the way there. It's going to keep the Q and the Q bar just where they were. So we can't predict what state they're going to be in, because they're just not going to change from whatever they were the last time there was a falling edge and there was something other than 0, 0 on the input. So we load a 0, so if we make the K input high and the J input low, and put a falling edge in, then that's going to force the Q into the low state and the Q bar into the high state. If I flop it around, put the high state on the J input and a low state onto the K input, I'm going to force it in the other direction. Force the Q output to be a high and the Q bar output to be a low. And if I bring them both up high, I get, oh, this somehow lost. Yes, okay. So this becomes Q bar and that becomes Q. So this is the same with both inputs to the J and K tied high. We've got the same functionality that we had with the D type when we wrapped the Q bar around to the D. So it becomes a toggle flip-flop. But with the JK, we've got 4 possible things that we can cause. We have 2 input lines. 2 to the 2 is 4. So 4 possible things that we can make this device do. We can cause the output to always change state on every input pulse. We can cause it to force the Q output high, the Q output high and the Q bar low. We can cause it to force the Q low and the Q bar high, or we can force it to simply hold whatever is the current state. So essentially ignoring the state or the active transition on the clock. Yes. So when I have the J and K inputs tied low, and I have an active transition on the clock, then the Q is going to hold whatever state it was in before. That's the little q is the state of the Q output before the falling edge. And the Q bar is going to hold the state of the Q bar before the falling edge. So it effectively ignores that falling edge. It doesn't make any change in its outputs. Question? Yes, Indu. What? We're ignoring those. Next time I'll take them out of the table. When you buy a discrete flip-flop, it will have these extra pins that allow you to force the output, the Q to be a 1, or force the output, the Q to be a 0, independent of the clock pulse, so that you can initialize it into some known state. Okay? We're not going to, as I say, not going to design with these things. And having the set and reset inputs on functional schematics is relatively rare.